So I turned DevTools into a 3D renderer, and I'll be walking you through a 10-minute coding time lapse explaining how you, dear viewer, can make your own 3D renderer. We'll start by creating a blank page with the only thing in the body being a script. We'll put the majority of the code in a separate file, and a good place to start is by making a vector class. The constructor will take the x, y, and z coordinates. We'll also add a w component for translation. We'll need some methods for adding, subtracting, and scaling. This will be useful for drawing triangles and, later on, a matrix class. We'll make use of dot products to get the length of a vector, which is also needed for drawing triangles. Now, another important class to make is the viewport. Basically, it'll hold a buffer of characters. We'll use the width and height from the constructor to create the buffer. Next, we want to draw triangles with a buffer. Each vertex of a triangle will be in normalized device coordinates. We'll use the vector methods from earlier. In a triangle with vertices A, B, C, we'll subtract to get a vector from A to B and from A to C. We'll also need the lengths of those vectors. Using barycentric coordinates, we'll find all of the points inside of the triangle. Starting at one of the vertices, for example a point inside a triangle is represented by adding some combination of the two vectors from A to B and from A to C. These vectors are scaled so that the sum of the two scalars is between 0 and 1. Then we take the point from the triangle and normalize device coordinates to a row and column of the buffer. If the fragment is not clipped and passes the depth test, then we'll overwrite the previous value in the buffer. Afterwards, update the scaled vectors at the end of the loop. Now, we'll work on displaying the buffer. Take each row, turn it into a line, and join it with new lines. It's time to draw some triangles. Remember, 0, 0 is in the center. We can also try reducing the height of the viewport. Generally, delta should be updated on resize. Anyways, let's try drawing a triangle from the bottom left corner to the top right corner. Now, we'll need to make a matrix class. We'll be making it column major so that transforming vectors is easy. Because whenever we transform vectors, all we need to do is to take a linear combination of the columns of the matrix. For our transformations, we'll make it compose a pre-existing matrix with the transformation. So for translation, you'll notice the fourth column is affected. For scaling, you'll notice that the first 3 columns are affected. Next, we'll create a matrix for a right-handed symmetric perspective view frustum. The field of view angle in the y direction determines the height of the plane. Half of that angle will give half the height. When multiplied with the aspect ratio, we also get half the width. Dividing by half the height will give us y coordinates from -1 to +1 after perspective division. A similar transformation happens to the x coordinates. Our projection scales and translates z coordinates so that the near and far clip planes correspond to z normalized device coordinates of -1 and +1 respectively. We'll also need perspective division, so we make the w component hold the depth. Next, we'll add a function to multiply matrices, allowing us to create composite transformations. This will be important for our camera. However, first, we're going to need a model to transform. For simplicity, our model will be a cube. It's good practice to separate vertices from elements, so we'll make two arrays. Notice the vertices have one as a W, allowing us to translate them. For the elements, we'll use X, Y, and Z as indices. Its W will be a character used for drawing the triangle. We can now start with a basic camera that will test out the new matrices on the cube we've added. That is, the projection, translation, and scaling transformations. We'll compose these transformations into a single matrix. Then, we'll create a method to transform vertices with this matrix, and also perform perspective division. Now, we'll adjust the viewport to take in the field of view angle and the aspect ratio of the characters in the buffer. The overall aspect ratio used by the frustum would be the viewport width divided by the height. However, because the characters are not square, we need to also multiply this with the character aspect ratio. The render method uses the camera to transform the vertices of a model to normalized device coordinates. Then, we'll use the elements of that model to draw the triangles that make up the shape. To test the render method, we'll create a viewport in a list of models. We may want to add models transformed by some model matrix. We may want to remove models. Our main method will clear the viewport, render all the models in the list, and log the viewport to the console. When we call main, we see our cube. Let's add rotations. We'll modify the camera to take in some angles based on the current time. The roll matrix rotates the XY plane. As we are composing this matrix, notice the first and second columns are affected. The pitch matrix rotates the YZ plane. As we are composing this matrix, notice the second and third columns are affected. The yaw matrix rotates the ZX plane. As we are composing this matrix, notice the third and first columns are affected. Now, for testing, we'll add some rotation to the camera. Let's put roll before translating. We can call main to see a rotated cube. Now, try calling main through setInterval. The cube rotates counterclockwise. Let's try pitch. We'll call main the same way. The cube rotates towards the camera. Let's try yaw. We'll call main the same way. The cube rotates on the ZX plane. Let's try two rotations at once. For anybody following along, You should now have some starter code to play around with. I hope you learned a thing or two about vectors and matrices, the fundamentals of 3D computer graphics. I'd like to thank today's sponsor, These Nuts. Now, if you haven't heard of These Nuts,